When we say to make an argument, what do we mean? Yes, sir. Huh? Well, I'll just use your test to assess that. And so whatever you score on the test with those questions will replace that understanding check grade. Now, you can leave, but you're also going to miss the instruction on the concepts you missed while you're out. So I would take advantage of that. Okay? Don't log in right now. System, I messed up something earlier, but it's fine. When we say to make arguments, what are we trying to learn how to do?
Like, rebuttal someone else's answer and trying to understand how they got there.
Okay, and then once we try to understand how someone got there, you need to make your own arguments, which means you need to either, it's one of the two questions I regularly ask, you either need to add on to or push back on, right? You need to make your own claims. Do you agree with that claim? I thought you said you left it in your car. Well, if you have another one, it's got to be put up.
I can't put it in.
Why?
I can't put it in.
Why can't you put it up? Okay, we're going to talk about this in a second then. So, we need to learn how to make arguments. So we need to learn how to listen to people's ideas and either add on to or push back on, because what is required in order to do that?
Thinking.
We got to learn how to think. And if we learn how to think, we're also going to learn how to grow. And if you learn how to grow, the sky's the limit. You can constantly grow and do more. So keep that in mind, that we are trying to learn how to think in the context of mathematics. Because what is math is going to be a huge part of today's lesson. What is math? It's the study of something. Patterns and relationships. That's the whole thing of today. Alright, so let's go over this understanding check. I've put the answers up here. So what specific questions do you have for this very first one here? Hayden, I need the hood off, please. What? Say again. There should be a blank one right there. By the way, guys, I've already made scans of these. I will grade off the scans. You can write whatever you want on there. There's colored pencils and markers underneath the desk. So write whatever you need to improve your understanding. Now, hear me clearly on this. If you did not understand how to get these answers, which I think that this is one that we should be able to get, but I understand why there's difficulty for students. Is it enough to just write the answer down if you want to use this to prepare for your test? The answer should be an emphatic no, because you have to do what to be able to do a different problem that's similar? You have to understand it, guys. So make sure you write down the reasoning and the thinking of why these are the answers. So why in the world did I get these x-intercepts for h of x? So, say again?
G of x is y.
So g of x stands for y. And so how does that inform me where I'm going to have an x-intercept for h of x?
When the y is 0, it's x.
Okay, when the y is 0, we have x-intercepts, right? And so if h of x is f of x times g of x, we haven't looked at it much like this notation, but we have talked through it. Like, for example, if I had x plus 2 times x minus 3, if this is a 0, right, isn't that going to make the whole expression 0? Because of what key property? The zero product property, right? That's the zero product property. So the fact that I have a 0 here, an x-intercept here, that's going to make h of x what? A what there? A 0. That's it. Yeah. It makes it a 0. It makes an x-intercept. Similarly here. Now I want to point this out. The other way that you can clearly see it is in order to calculate h of x, someone already mentioned f of x stands for what? The y for f. And g of x stands for the y for g. And so what am I literally doing to these y values? I am, so h of x, if x is -3, h of x is 72. If x is -2, h of x is what? 27. Just multiplying the y values. For h of x, when x is -1, what's the y value? There's an x-intercept. There's an x-intercept. All that notation means is that we are multiplying the y values. Remember, and a lot of y'all for later, no, it's not this question. It's the next one. Okay. But we need to notice we're just multiplying. And everywhere that f of x has a 0, h of x is going to have a what? Well, it's going to have a 0. If f of x has a 0, h of x has a, if g of x has a 0, h of x has a 0. Guys, that's the whole point of this factor notation, is that everywhere one factor has a 0, the dilated function has a what? 0. That's it. Please note that language. Even though I didn't write that on the board, that's the key idea, that everywhere one factor has a 0, the dilated function is going to have a what? 0. Wherever one factor has a 0, the dilated function has a 0. Now we got to move a little bit quicker through the rest of this. But that was, I think, the most unclear question on here, but that is a concept that we had talked through. This required you to apply the information we had talked through. Number 2. Before I put it up there, what specific questions did you have? I mean, there's colored pencils right there, right?
I like the way that you
I know, but people kept stealing my pens. I went through like 2 whole packs.
No, I'm not feeling this pen. I'm not going to steal it.
I know, Billy. Everyone says that. I don't know. I'll think about it. Try the marker or the colored pencils first. Specific questions about number 2. Cool. Raise your hand if you thought that there was 0 x-intercepts for number 2. Okay. What about 1 x-intercept? Anyone say 1 x-intercept? Okay, we got one person. 2 x-intercepts. I think that was the most common response. Anybody say 3 x-intercepts for number 2? Okay. So what was our reasoning for 2 x-intercepts? 2 and 3 were the most common responses. Guys, notice this is the explanation of why. You got to engage in the understanding of why. Why did we say 2 x-intercepts? Oh, you said 3. 2 x-intercepts. Anybody? Yes, ma'am.
I said I don't have two things, so just that.
Because why?
So
There's 2 x's. Okay. And then Aisha, you said 3. Why did you say 3? So g of x was equal to x times f of x. So let's think about those arguments. We've made claims, we've provided evidence. So what's the correct answer based on that information that we've looked at? What do we think? Aisha is convinced of 3. Liza, what do you think about Aisha's claim that we have to look at the x times the f of x? Okay. But have you considered Naisha's evidence? Because when you say there's 2, which function are you looking at? What does it say? To the left of those 2 expressions being multiplied. What does it equal? Okay, so that says f of x. What does the question ask about? How many x-intercepts does what function have? G of x. We need to notice a key language here. Something that we are forgetting is that word dilated means that we are doing what mathematical operation?
Multiplying.
We're multiplying. Dilated means to multiply. Notice f of x had how many zeros? 2. But if we dilate by x, what are we doing? Right, but in terms of zeros or x-intercepts, we are creating how many? Well, how many is this dilation creating? How many? Just one. So we already had two, and that's what you're looking at, Eliza. But when we dilated, we created one more. Notice, I identified what each of those zeros are. There are 3 zeros, so how many x-intercepts? 3. Every real zero corresponds to an x-intercept. That's what we would want to notice out of this question. That keyword is dilated, and I asked you to look at which function? G of x. What if I had told you that that f of x is dilated by x squared minus 5 times x plus 1? How many x-intercepts do we have now?
4.
We already had how many with f of x? 2. How many x-intercepts would we have here?
2.
2. And here?
1.
So that'd be 5. What if I had said, hey, I'm going to dilate by x squared minus 5 and x plus 5? How many x-intercepts now?
Be the same. 6.
Because while this is a 0, and I would have 5 zeros, aren't those zeros the same? So that would be what kind of point? A double root. So even though there's 2 zeros there, how many x-intercepts would that count as? Just 1. That's something we do need to pay attention to when you have a double root. Right? It'd be the same x-intercept. You're not going to count those x-intercepts twice. You would count the zeros twice. That's a key idea to pay attention to. Number 3. Most people recognize that's the first one. This third one should be a quick one to know why it's not the third. It only has 2 roots. Notice if we have 3 zeros or 3 roots, what type of function is that? At least a cubic, which is degree 3. This is only degree 2. Yeah. So why is it not the second or the fourth?
The second one got 2 positive roots and the other
So we want to notice there's 2 positive roots. Up here we had how many positive? 1. So why not this one? Yeah. That is one that is tempting for some students, but I want you to consider this. This is further to the right than this one is to the left. But that's negative 5 and that's positive 3. Can the positive be further to the right than the furthest to the left negative? So we would want to consider those things. We also want to consider putting up our iPads and not watching boxing. And I'm teaching, so we don't have our iPads out watching boxing. Okay. Any lingering questions for number 3? So number 4. Y'all made that number 4 way harder than it has to be. If you see the word dilation, what operation should you immediately think about?
Multiplication.
Multiplication. So we dilated f of x by what? By x minus 3. So literally, f of x times x minus 3. Right? That keyword dilate tells you to multiply. Notice, I didn't ask you to distribute. All you had to do is write it as factored form. Where did x plus 4 times x plus 2 come from? From f of x. F of x is x plus 4 times x plus 2. So that's where g of x comes from. Notice I did not show the justification. You need to think through and justify those things, or write it down as we talk through it. Yes, Tyson?
How do you change it to stable, bro?
So, okay, that's a good question. That is, Tyson, were you here Monday? Okay. So it's using the concepts that Mr. Kilpatrick taught us on Monday, and we can look at that one really quickly. Zeros, notice again, I did not show the work. That is not enough justification in any way, shape, or form. That would only score a 1+ from the rubric. But how did I find my zeros? So substitute 0 in for g of x, use your zero products property, and set each factor equal to 0, and solve. That's it. Okay? That's something we do want to pay attention to. I'm going to go quickly through C because I know some of us have missed that instruction. Now, for those of us who have been here, first things first, when I am multiplying, yes, you can distribute, but what strategy did we learn from Mr. Kilpatrick to make it easier to multiply? What's that little box called, though? So if I have a rectangle and I want to find the stuff inside of that rectangle, what am I looking for? The area. So we call this the area model. Guys, we got to know our vocabulary. I was talking about that with someone who came to tutoring this morning. If you don't know the vocabulary in mathematics, it is hard to communicate. If you don't know the vocabulary in mathematics, when you read a question that asks you to dilate something, you're going to get lost. You've got to know your vocabulary. When they use that language in the book, you got to know what it means. Yes, Taisha?
How many points would turn out like with G of X?
I don't count points off. You show me evidence of understanding. Now, if you did not write g of x when I asked you to write the dilation of f of x as g of x,
No, not that one.
oh, for here,
Procedure.
but I again asked you for the standard form of g of x. I guess just writing this without the g of x, I would consider that a missing detail that's kind of important. So like a 3D, maybe a 3D plus, but probably a 3D, which is still good evidence of understanding. I would consider that to be correct, just you're missing an important detail. Now, for those of y'all who missed, y'all need to pay attention to this. Guys, how many factors can you multiply at a time? 2. Only 2. You can't multiply more than that, so don't try to do all 3 of these at the same time. I'm going to set up my area model. When I do my area model, you can follow the way that Mr. Kilpatrick and Ms. Bauer did it. I like the way that the book sets it up. For each factor, I'm going to do a row and a column. And what am I going to put in this top left corner? Multiplication symbol. It helps me recognize that I'm multiplying. Now, what dimensions should I do if I'm trying to multiply these factors? 2 by 2. 2 by 2. So x plus 4. X plus 2. That's it. And then we multiply. What is x times x? X times 4. 2 times x. And 2 times 4. That's just distributing, but it's a way to help us. I'm going to identify my like terms. Plus 6x plus 8. But then remember, I still have that x minus 3. And now I have 2 factors that I can multiply again. What dimensions would I need for my area model this time?
3 by 2.
I need a 3 by 2. I'm going to do my x minus 3 here. I'm going to do x squared plus 6x plus 8. And distribute x cubed minus 3x squared plus 6x squared minus 18x plus 8x minus 24. Like terms. So I got g of x equals x cubed plus 3x squared minus 10x minus 24.
Do you gotta put a place in front of it?
You don't have to, but what are you doing with every single term? Right. So is it helpful to go ahead and put that plus there to identify that it's positive and that you're adding? It's helpful. Necessary, no, but I think it's helpful. I do recommend it, but it's a recommendation, it's not a requirement to show evidence of understanding. Questions up to this point? Tyson, does that answer all your questions there? Okay. Ethan, I know you're gone, but does that start to make sense with multiplying? Okay. So there's practice problems in the book. We did them together in class and went over them. Some Monday, some yesterday. Questions, comments, or concerns through number 4? Remember, and this is something, guys, that came up during tutoring as well. I need you to remember that the point of class is to learn, not to do assignments that we get hundreds on because we completed the stuff in class. It's to learn. Show me your understanding on assessments. That's the majority of where your grade comes from. The learning happens every single day. You got to engage in that learning and thinking process. Now, on this next slide, I need you to hear me very clearly on this. It is not enough to have the general shape. When you sketch it, what key points do you have to go through? You have to go through the zeros. You got to pay attention to that. And you cannot go through the x-axis unless there's a zero there. So look at your graph again. Are there any points on your sketch that go through the x-axis not at a zero? That's something you want to consider. Next, here's what it should look like. One thing that you want to pay attention to that I know messed some students up, when I look to the left of the zero, remember I like that dashed line to identify that zero. Some of y'all said, hey, that's a positive times a negative, which is what? Negative. However, how many factors are there? 3. Here's that third factor. And that's going to, that's hideous. That's not a line. And it's going to continue and continue and continue. And so to the left of that zero, are these factors positive or negative? Those are negatives. And so notice positive. So up here, positive values. Down here, it's below the x-axis. These are all going to be negative times a negative is positive. That is why all of these values are positive. And why is the graph decreasing even though we have positives? It's got to get to that zero. Why does it go through that x-intercept? Why does it go through the zero? Because it's what? Contrast that to over here. Notice it doesn't go through that zero. It touches and bounces off. Well, this one's a double root. This is a single root. Notice how many factors go through that zero. When it's a single root, it just goes through, and that's it. And so we want to notice that it goes through. And we can also see a positive times a negative gives me a negative set of values. So it's negative, and then it comes back up to get to the zero. There are 2 linear factors going through there, so it's a double root on top of the fact that these values are positive, these values are positive, and then this linear factor has negatives. And if I have positive times a negative, I get a negative. What questions do you need to ask before we continue? You've got to understand, and you need to take notes to understand. Or at the bare minimum, take a note to yourself. Hey, we went over this on April 26th in the first 30 minutes of class. That means you can go and watch that video again to make sense out of these ideas or to review things like that. These are critical ideas to understand before we move forward. Questions, comments, concerns? Again, it's not enough to just have the answers. You have to understand why, and you make notes about those things. At this point, go ahead and get your textbook out. We are going to look at lesson 3 very, very, very quickly and talk through a couple of ideas. Lesson 3 starts on page 139 of the book. Haley got new groups. Anyone know what group Haley was in? She was right there. So, you say it's still your birthday? Your birthday was yesterday. So, ladies and gentlemen, this is a key idea to remember. What concept will 100% show up on your test? Fundamental theorem of algebra, which tells us that what two things match each other? The number of roots and the... Well, roots and zeros will always match, but roots and the degree, right? Do not forget that the number of roots and the number of, or in the degree will always match. We can clearly see here that there's how many zeros? 3. So what's the degree of this function going to be? Third degree, right? A degree of 3. So it'll be a cubic function. Yes, 139. Okay? Because when I say 139, I'm looking at this Exploring Cubics lesson. And hear me very clearly on this. We're going to move quick. 139 is, we're going back to lesson 3. Oh, I lied. Apparently I messed up and didn't update that page number. We are on page 53. Thank you. Yes. Okay. So this lesson is all about what type of key functions? What key functions? Cubics, right? Specifically, we are introducing the key characteristics of a graph that you need to pay attention to. And so these characteristics are going to tie into the next set of lessons that we look at. What are some key characteristics of all graphs that we know we got to pay attention to? We are going to think about concavity, but when we start getting to these cubics, concavity will change. What else? X and Y intercepts and zeros tie into which of those points? X-intercepts. Okay? What other features of a function? We haven't talked about them as much, but you did do a Matthew assignment on them. You talked about them in Algebra 1. Say again. What is that thing right here? Relative minimum. And so then you would also have a relative maximum. So those maximums and minimums, those are known as the extrema of a graph. Yes, 100%. That's something else. What, does anyone know what the collection of all the x values for a function would be called? Starts with a D. It's the domain. We haven't talked about it much this year, but we got to always consider the domain of a graph. That's the set of all inputs, which means we also need to consider all the outputs, all the y values, called the range, okay? So we're going to start introducing the language for that. It's going to tie into next unit. We're also going to, in the next lesson, talk about what's called end behavior, and we're also going to talk about increasing and decreasing. So we already looked at this situation where we took a box, we cut out the corners, and we folded it up, and we looked at the volume, and we found out because we had height, width, and length, the volume followed what type of function? That volume was what type of function? Well, so remember, the height was linear, the width was linear, and the length was linear, and if I multiply 3 linear factors, cubic, right? We had 3 zeros, a third degree, we had a cubic function. And one thing I did point out is if you have a cubic function, what rate of change, what type of rate of change did you have? So it wasn't, what type of function had constant additive rates of change? A linear function. What type of rate of change did a quadratic have? A linear additive rate of change, right? 1 degree less. So a cubic had what rate of change? So remember, linear had a constant rate of change, which is understood to be x to the 0. A quadratic had a linear additive rate of change, which is x to the first. And so a cubic has what? A quadratic additive rate of change. Remember, the rate of change for a polynomial is always 1 degree less. The rate of change is always 1 degree less for a polynomial. Now, here's the concept that we need to talk about. We started to fill out A here, but we did this by looking at the graph. So to talk about these things, pick up your calculator we need to graph this function. So following number 2, you don't need to be logged in to create a graph. So just go to add graphs.
You take me understanding shit back up.
I already made scans of them, so I have copies of them already. So those are for y'all to learn from your notes. So remember, it's a learning activity so that we can be prepared for assessments. Okay? So what function do I need to put in based on what the book says? Or no, we had it written up here. What's the volume function?
It's still not.
You don't have to log in to create a graph. You just have to create a new document and pick a graph page. Okay, so v of x, which is, it's up there in blue, x times 2x. Okay, if you can't see it, here's a little bit bigger. One thing I want to remind you is the way that the calculator is set up. You have to put the multiplication symbol right there to multiply. So, x times 2x minus 18, no, negative 2x plus 18.
You gotta change the F1 of x to the V of x.
No, you can leave it as f1 of x. Actually, you should leave it as f1 of x. The calculator won't accept anything but that. That graph should look hideous. We do see the right 3 zeros. But make sure that you you hit menu, and then you're going to change the what from menu. I'm going to go to Windows/Zoom, and then Windows Settings, and put the Windows Settings based on the book for number 2. By the way, we should be on page 157 right now. So notice the Windows Settings. It says that the x values need to be negative 10 for the x min, 15 for the x max. The y values need to be negative 400 to 400. Okay? Type in your equation. No? The equation's right there for in red. So we need, was it negative 10 to 15? And then the minimum y is negative 400 to 400. Once you have those typed in, just like that, hit enter, and that's a way nicer looking function. Okay?
I ain't looking at nothing right quick. I don't know why I'm putting it.
So check your graph.
Where'd you get that from?
Can I see this real quick?
Hold on.
That's right. Remember, oh, hold on. That's the issue. No, you changed the window wrong. Negative 15 to 15. Don't just zoom out. Nope, negative 10 to 15. Remember, it's what's in the book. And then the book says negative 400 to 400 in the y. Okay. So, what is the maximum volume of a planter box? State the dimensions. So we talked about this, I believe, briefly. One thing I do want to remind you of, we're talking about volume here, right? What type of volumes can you not have?
Negative.
Can't have negative volumes, right? Which also should make sense. Can you cut out less than 0 on the squares? No, right? And then so, notice this would be the only piece that I'm really looking at here, because after that we get into the negatives. So I taught y'all a quick little thing on the calculator. I think this is the only class I got to. Part B asked for the maximum, right? Does anybody remember how we can find the maximum using this calculator? Because it's a really powerful tool. I'm always going to hit menu. Now think about what features there would help me find a maximum. We're trying to analyze that graph. So hit Analyze Graph. What are we looking for? Maximum. Okay.
No.
Hit menu first. And then click the number for Analyze Graph. Now remember, lower bound, what does that mean that vertical line needs to do? Go to the left of that maximum. So use your touchpad to go to the left and hit enter. Upper bound, maximum. Upper bound needs us to go to the right and hit enter. And so which of those values is my volume?
First one?
Why do you think it's the first one?
I lied, it's the second.
Why is it the second one?
I don't know, we go in the book.
Is my volume
Oh,
the
wow.
input or the output?
Output.
That's the output, it's my y. That's something we gotta pay attention to. So the volume is 228 cubic inches, and so then what's the x, what's my input? And remember, x was how much we were cutting out. So the square, the length of the cuts, right? So a cut of 2.35 inches yields a maximum volume of 228.16 cubic inches. This is something that I'm going over because this is an important idea. The idea of maximum and minimum, by the way, we should be on page 157, no, part B. The idea of maximum and volume is something that will go through Algebra 2 into pre-calculus, if you take pre-calculus, into calculus, if you take calculus. The idea of a maximum is a critical idea for the rest of mathematics if you go beyond Algebra 2. And until calculus, you will not know how to find that volume without a graphing calculator. Miracle, you engaged? You look like you're zoned out. Can't learn that way. We gotta be focused. Yes, Jalen. That would go under B. Yes, ma'am. Because doesn't B ask you for the maximum volume? Right? Now C says identify the volume for V of H, which they're using the variable H because that was that height. So look at your graph. I already mentioned it, and y'all need to define this. Domain is a key vocab term that you've got to know. What do I mean by domain? So it's the set of all, not x-intercepts, x values. So it's every x value that graph has, which remember our x values are also called the inputs. I'm going to show you an important notation that we should have seen, but it might have been a hot minute, or it may be brand new, but it's a very straightforward notation. And it's called interval notation. So there's the definition of domain. We're going to use interval notation to show domain. And so the way that interval notation works is you'll either use parentheses or you'll use brackets, but you'll just put a minimum value, you'll put a comma, and then you'll put a maximum value. So you'll put the absolute minimum x value and then the absolute maximum x value. So looking at that graph, because I'm only going to ever ask you to know this off the graph, what is the absolute lowest x value, the lowest input that we could have for v of x, that function? So, so one thing to clarify, not based on the context of the problem, for this function in general, which I'm going to use the entire graph to think about this one. So remember that negative 400, was that x or was that y?
That's why.
That's why, so keep that in mind. But also, that's the minimum here, but what do we know about this curve? It's going to keep going down, right? But remember, down, is that an X or a Y idea?
Why?
That's a Y. But if it keeps going down, it's also going to keep going to the left. Is it ever going to quit going to the left? So what is the lowest Y value if it goes to the left for all of eternity? It's, what do we call it, Ethan? Negative infinity. Jose, you're going to say it doesn't, right? And so to represent this idea that it never stops, that it goes for forever, the minimum value would be negative infinity. So the minimum x value for that domain is negative infinity. Preston, you with us, my man? Tell me, why is that minimum value there for the domain negative infinity? It's the lowest x. It's never going to quit going to the left. Say again. Okay, so Grace is making the claim that she thinks that the maximum x value would be positive infinity. Yes or no? Anybody want to add on to or push back on? Add evidence to it or push back on that claim?
No,
Yeah?
I mean, wait, what'd you say?
Do you want to, so Grace's claim is that the maximum x value would be positive infinity. Does anyone want to add on to providing evidence for or push back on that maximum x value?
I don't think you want to push back, I think that's right.
You think that's right? So what's our evidence for that idea?
It ain't gonna stop.
It's not going to stop. Now, and then you talked about it's going to keep going to the right and it's going to keep going up. Which of those ideas matters for domain? It is going to keep going up, but is up an x set of ideas? No. So it's going up and it's going to the right. That's an x, so is it ever going to stop going to the right? No, so the maximum x is positive infinity. Now that's for the function. But Ethan, you pretty quickly were like, oh, it's 0. Notice C says, is the domain the same or different in terms of context of the problem? Tell me, when we talk about those cuts, can you have negative infinity in the terms of the cut? What's the lowest amount that you could cut? The lowest you could cut is 0. What's the maximum amount you could cut? Now that was the maximum volume, but is that the maximum you could cut? Tell me, when can I stop cutting?
Why when you get right there?
Where is it? Right here?
Now it's mine.
Okay.
I always could. It's right there.
Right there.
Right there. Notice after that cut, we start getting into what set of volumes? That's not possible, right? What's that point there? Sounds like we're guessing. How about this? It'd be nice if the calculator had a way to identify that point, isn't it? It is. So, what are we going to do? We're going to hit menu. Look at the options. What are we going to try to do? 7? What is 7? What is 7? Oh, I'm going to analyze that graph. Anybody see one of the concepts here that would identify that type of point? It's an x-intercept with, not intersection, but an x-intercept is also called a what?
0.
Oh, I'm going to go to 0. And what's it ask? Lower bound. That means that vertical line needs to be to the left of the, what's the thing you called? The 0, the x-intercept, and I'm going to hit enter. Upper bound means it needs to go to the right, and then I'm going to hit enter. So what's the maximum amount we could cut? 6. So from entire function we have that, but from context, what's the minimum cuts that we can make from context? 0. And the maximum? 6. Remember I said you can use brackets or parentheses. We're going to talk about that idea more later. And technically that could be brackets or parentheses based on the way you define it. Use brackets when you can equal that value. And so technically, could I cut 0? No, but like kind of yes.
What you mean by equal?
So is it an actual value that is possible? Can I actually do the thing? And the answer is yes. Could I cut 0 centimeters from the corner? Or 0 inches? Yes, I'm just not going to make a cut. If I cut 6 inches, it would just cut it in half and I would have nothing. So if it's an actual possible value, does anyone remember where Cam was? Right in this group? Okay. Well, that's Jalen, right? No, Jalen, was that Shania? Shania was right there. So we want to notice that if those values can be equal. Now I'll point out, can you ever get to an infinity?
No.
Have you ever met anyone who's reached to infinity if it goes forever and ever and ever and ever?
No.
Yeah, I know Buzz Lightyear likes to go to infinity and beyond, but even then, I'll be honest, I always think about Buzz Lightyear when I talk about infinities. But even then, obviously, he hasn't gotten to infinity because he keeps going. Infinity goes beyond that, right? So, you can never equal infinities, that's why we put parentheses. So when a value can be equaled, we put a bracket, can't be equaled, infinities. I'm not going to test you on that yet. That'll be within the next unit, but that is a good little intro. I will point out, where did that 0 come from based on this equation?
The fact.
From this one, right? I set that factor equal to 0. So negative 2x equals negative 12. And so x was equal to 6. So, does the domain change based on the context?
Yes.
Yeah, remember we went from those infinities to 0 to 6. Alright, so part D says identify the range. How did we define range earlier?
Set of all y values.
Okay, so D, the set, so range, set of all y values, and those would be my outputs. Anyone know what notation we're going to use to indicate those values?
Why?
Well, we're looking at the y values, but what notation? That interval notation. One thing I will point out, I don't know that I said this clearly earlier. When I say minimum value, comma, maximum value, that comma means everything in between. That's why we say an interval, because that's the lowest value, that's the highest value, and we get everything in between. If you don't have everything in between, you can't use that notation. When we talk about the cuts in context, I could cut 0, that's the minimum. I could cut 6, but could I cut any number in between? Yes. And so that's why we put that comma there to indicate it's everything in between. Now looking at this function here, this graph, what would be my minimum value for the y? You have your book with you?
Yeah.
I'd get it out. Remember, we're talking about the entire function. Not in context, but the entire function.
Oh, negative the thing.
Why? What's your claim is negative infinity? Where's that coming from?
It don't stop.
It don't stop doing what? Remember, y is going to be down and up. So I'm going to look down first. I want the minimum first. Guys, hear me very clearly on this. Students mess it up all the time, where they put the maximum and then the minimum. Can't do that. It's always minimum, then maximum. So it goes down for forever. That negative infinity is my lowest y value. What's my highest y value? Infinity? Infinity? Not infinity?
It's infinity.
It's infinity? Yeah, maybe? What's your evidence?
Keep going up. To the right, keep on there.
So the far right side, it keeps going up. Is that true? So what's the highest y value? If it keeps going up forever and ever and ever and ever? Infinity. That's my domain. Or sorry.
Range.
Thank you. Yep, that is range, not domain. Now, it does match the domain, but we gotta talk about x versus y. In the context, looking at D, is the range and context the same?
No, I mean, wait. No,
Remember, this was the lowest that we could cut.
it's not.
So what's the lowest y value?
Zero.
That's the x-intercept. The lowest y value in context is 0, and you can have a volume of 0. And what's the highest y value? I would say, remember, that was an x value. Say that again, Ethan. 228.16. Remember, that's that maximum we talked about earlier, comma, 228.16. I'll point this out. Can you actually have that volume?
Yes.
I mean, that's literally a point on the graph, is it not?
Yep.
So can you have that volume? So if I can have that volume, if I can equal that value, I need to put a what there? Bracket, it's a joke. A bracket. Brackets are when you can equal that value. Note on E, it asks the question, what do the x-intercepts represent in the problem situation? Well, it's an x and a y. What do we know about the y values for every x-intercept that's ever existed?
Zero.
What is 0? Did I already say the y?
Why?
Yeah. The y values are 0, thank you. And so remember, y is representing my,
No,
what is v? In context.
Volume.
Volume. So those x-intercepts are where the volume is. Hey guys. I'm actually comfortable. I'll look at it in a second. But hold on. Guys, if I look at 6, 0, remember that 6 is my x. X represents what could be cut. Y represents the, what again? Well, the y is 0, so the volume is 0. Notice I'm just talking about the context. What does x represent? What does y represent? Y is the volume. Those x-intercepts, that's where the volume is. A big old goose egg, which is the number 0. Thank you. Okay, the x-intercepts is where the volume is 0. Guys, it's whatever the y is. The y is volume. At the x-intercept, the volume is 0. Can't say that any more times without you writing it down. You gotta write that down.
I used to say a regular is. A blue egg was, I thought it was vegan.
Huh?
Oh, no.
You thought it was what?
Nah, she was being vegan. That is not.
Okay. Now, this is where I need y'all to really pay attention. This is on the very next page. Okay? And then we're going to jump to the next bit of the lesson. Please notice, we're going to talk about absolute max and absolute min in a second. The points that we are looking at are relative maximum and minimum. And here is why. This point, is that a maximum, is that a peak for its section of the graph? Yes. But are there y values that are higher than this point? Remember, over here, the y values go up to what? Infinity. So is that the highest y value for the entire graph? No. Remember, it goes up to infinity. So are there y values higher than 228? Yes. So if it's the highest for its section, but not the highest y value completely, we would call it a relative maximum. Is that higher than all the y values around it? Relative to the y values around it, is that the highest? So it's a relative maximum. If you think about a roller coaster, we've all seen a roller coaster. Hopefully we've enjoyed the joy, or experienced the joy of going up a roller coaster. When you get to that highest point of a roller coaster, it's the maximum. Now, it may not be the highest point for the entire roller coaster, but it is a highest point for its section. And that's what we mean by relative maximum, is a highest point in a particular section of a graph. And a key idea that I do want you to notice is this. We've actually already talked about it. In between zeros, that function is going to have to increase and then start to, and the point where it starts to decrease is called a, what type of maximum? Relative maximum. So, one of the big things that we need to notice is with a relative maximum, one, it has to happen in between what points? Zeros, right? It's got to increase into the positives, but it's got to start to decrease back to the 0. So, they are in between zeros. There's just an extra note. They're in between zeros when the function stops what? It's going to stop what there? It's going to stop increasing and start decreasing. One thing you need to note and pay attention to, when we say increasing and decreasing, what values are we talking about? The x or the y? What's going to stop increasing and start to decrease? But what, the x or the y? The y values. I need you to pay attention. You see how I'm always going to the right? You read a book, or you read a graph like you read a book. What's the x value always doing? The x is always increasing. When we say increasing and then decreasing, we're talking about the y values increasing and decreasing. Then, in between these two zeros, it's going to stop decreasing at some point and start to increase. What are we going to call this point where it stops decreasing and starts increasing? Relative minimum. So a relative minimum is the lowest point in a particular section of a graph, and it's going to be between what key points? Usually, I will say, it could be a double root, but in between zeros when the function stops what? Decreasing and starts increasing. Please hear me very clearly on this. We're going to skip the rest of this lesson, but these key definitions are going to show up within the next set of lessons. So we are going to have to, one, study this vocabulary and know what these things mean. And two, if you don't know it in class, you need to come back to it in the textbook and use this information. Key ideas that we have got to know. So we're going to skip the rest of this, sadly including this piece, because we got to get moving. We might come back to it if we have time before our test. So here's what we're doing at this point. We're going to have a lesson on what's called in behavior, and this is a lesson that my placement student last semester came up with, and it was fantastic, way better than what the book has. Now, you should all have 2 sheets of paper. So get it out and let's look at it.
We done with the book.
Yes, I'm going to make a note about what lesson this corresponds to in the book. But yes, we don't need the book. Now I will remind you, there's that key vocabulary, so you might want to keep your book near you. Now, make a note to yourself at the top where it says higher powers. make a note to yourself that this corresponds to Module 1, Topic 3, Lesson 1. Okay? This information corresponds to what's in the book for Module 1, Topic 3, Lesson 1. Now, we need to pay attention to this warm-up question that Ms. Estel created because it's going to impact our ability to do the rest of this lesson within our small groups. What is the difference between the degree of a polynomial and the leading coefficient? When I look at f of x right here, what's the degree? 5. That is, the degree is the what? Highest. It's highest what? Power or exponent, okay? So it's the highest power exponent. So what is the leading coefficient? I haven't used this word much, but we should know what coefficients are, and so it's natural to know what a leading coefficient is. Is what? No, the degree was 5, wasn't it?
So it's 7.
Not 7.
It's 18.
It's not 18.
You said coefficient.
I see where y'all are thinking about leading coefficient as the highest or the largest coefficient, but the leading coefficient is the coefficient on the highest power. The leading coefficient, literally think about that word leading, it is what's in the front. The leading coefficient is the coefficient on the highest power. So to make sure that we clearly understand this, for g of x, what is the degree? Anybody want to push back on or add on to the degree being 5 for g of x? We good with that idea? Highest exponent. So then what is the leading coefficient? Good. I need you to remember that the leading coefficient is the coefficient of the highest power. The traditional standard way to write this would be this way, where the exponents are decreasing. Okay? That's why the 3 would also be called the leading coefficient. Traditionally, you write it from highest power to lowest power. And so the leading coefficient there would be 3. I made it up. I made it these up to help us understand this warm-up. To understand the difference between degree and leading coefficient. Because you have to know these things to be able to do the rest of the lesson. Now, here's what's going to happen. You should, nope, you don't have it yet because I didn't pass it out yet. You all have, why didn't it not print earlier? Say again. Page 3, copy is 18. Let's print now. If it doesn't print, I'll have to write the equations up on the board. That's not what I need. Computer, why do you hate me today? Marshall's like, well, Mr. Kenny,
So
computers
funny.
are just of the devil, so they'll hate you every
You heard what
day.
I said?
Huh?
Huh?
Alright, so here's what I need us to do. Group 1, your equation is y equals 1.5 x squared minus 1.5x minus 9. That's group 1.
I got to go.
Group 2, so write these equations down. Y equals x cubed minus 4x squared plus x plus 6. Group 3, y equals negative 2x cubed minus 6x squared plus 2x plus 6. Group 4, y equals 2x to the 4th plus 2x cubed minus 14x squared minus 2x plus 12. Group 5, y equals negative x to the 4th plus 0.5x cubed. Guys, it doesn't take talking to write these down. So each group has a different equation. Only write down your group's equation. But write this on your paper. Y equals 2x, nope, negative x to the 5th minus 3x to the 4th plus 5x cubed plus 15x squared minus 4x minus 12. And group 7 has y equals 2x to the 5th plus 2x to the 4th minus 38x cubed minus 2x squared, because you're going to use calculators, so it doesn't really matter if it's a decimal or not, plus 180x minus 144. Okay, hear me very clearly. Am I ever going to ask you to graph from standard form on your own? That is a heck to the gnaw. What you need to do is use your group's equation, go to the vertical surfaces, and write down your answers for numbers 1a through 1g. Do your best to answer them in about 6-7 minutes. Yeah, I might adjust, but we only have so much time in class. So write down your equation, and you're going to graph this on your calculator and work with each other to answer the questions through number 6, or 1a through 1g. Notice you're just identifying the degree, you're identifying x-intercepts, how many times does the graph turn. Now, one thing I want to clarify is when Miss Estel uses that language of turning, where on this graph do we see turns? So what points are you referring to? At the what? The relative maximum and the relative minimum. So we're talking with those terms about the relative max and relative minimum. Okay? So let's get up to our vertical surfaces. Let's answer these questions based on graphing these in the calculator. Let's get up. Let's move. Come on, get up, move. I need us to look at this up here. And so we are going to try to find some patterns and relationships, because that's the definition of mathematics tomorrow. If you did not finish answering the questions on this sheet of paper, you need to do that tonight. What graph can you use at home to answer these questions? There's a graphing system. Now, you could also sketch out the graph on your paper, which you should already have. But guys, what's an online calculator that you can use to graph these? Say again? Maybe, but there's another calculator that I've shown you that's the best. When have I ever shown you photo math? Desmos. D-E-S-M-O-S. Desmos. We've used it in class. Listen, stop hacking and listen. We have 90 seconds. Hey, 90 seconds, and I need your attention on this. When I look at these graphs, we're going to try to find some patterns. And what I need us to pay attention to is we may have to zoom out to identify these details. If you were stuck on this part, when it says as your graph goes farther and farther to the left, what direction does the graph go vertically? So if I'm going to the left on this graph, vertically what's happening? Isn't that going up? So what y value is that approaching? It's approaching infinity. Here, hey, stop and pay attention. This is how we would say that. Y approaches infinity. You use an arrow there. When we look at the right side, as x goes to the right, what's y doing? Going up, so what? So I'm going to write y, then approaches with the little arrow, going up, positive infinity. Never equals, you can never equal infinity. There's definitely been some good learning today, but guys, we got to make sure we master this. We have a test on Monday. We have to test on Monday. Have a great rest of your day. We will wrap this up. This is the last major idea before our test.
It wasn't even a minute.
It's not working well with them. Oh, no. You haven't taken it. That's last Monday. No, that's last Monday. That's the unit test. Okay, hold on 1 second.
That just wasn't very few. For my
Really? Hold on 1 second. So let's do this. I'm going to use this hunk of garbage. You need to return it or I will have to come after you. It's my iPad that the school gave me. I think you have several that you still need to do. Maybe you did, and I haven't put them in the grade book yet. You email me. This is probably dead. Let me charge it and get it set up for you, and then come back. Yeah. Yes, sir.
Tomorrow?
Yes, ma'am.
When can I make a, not tomorrow, but when can I make a,
We're actually about to go over it, so what I need you to do is learn from it, and then when you take your test, I'll use your test to assess those skills and replace your understanding check grade. But you need to do the learning that you missed. Yes, we have new seats. No. Hold on 1 second.
Mr. King, is it all the units on the map yet?
No, it literally says in the directions for homework, just unit 1.
Oh, let's go.
Just unit 1.
And I finished my, the one from